Hi, next up we're going to show you rate of reaction. Actually, it's a very popular topic. In fact, every year you will see one question on rate of reaction. And so I feel that the understanding of this concept of this topic is so important. So I hope this video will benefit you. If you like the video, remember to click like. Today I'm going to teach you about rate of reaction. So what exactly is rate of reaction? In simple terms, rate of reaction can be represented as just speed of reaction. Means how fast or how slow the reaction is. So in any chemical reaction, we have A plus B that will give you C and D. Our A plus B are our reactants, and the C and D are our products. When the reactants react, they will form products, and from the products, many a time, that's where we can measure the speed of the reaction. Example, by how fast a certain product is formed, especially in your case, especially for combined science, most of the time, one of the product is probably a gas. But what if there are reactions where there's no gas that's evolved? Does that mean that there's no reaction taking place? No. What that we cannot see, we should use other tests to test it out. But for this particular purposes, we are actually saying that for reactions that will produce gas, we can use the gas as a form to measure the speed or the rate of reaction. So, imagine I place this chemical reactions or the reactants A and B on a weighing scale. In this conical flask, it contains both A and B. When I weigh this, I'm actually measuring the contents within this flask. Measure in kg. In the beginning, you have the maximum, which is the combination of both A and B mass. Eventually, they will slow down and they will go to a stop, and it will look something like this. The decrease in the mass actually is the evolving or the escaping of the gas that has formed as a result of the reaction. So that's why you will see a curve that goes like this. Now, what if I actually use a stopper to stopper this entire conical flask? How will this graph look like that? Well, the graph will look something like this. It will be a flat line. Why? Because total amount of total mass of the reactants that is reacted over here will completely be transformed into our product, and that is by the conservation of mass. That's why if I don't put a rubber and I don't stopper this portion here and it become open, the gas will escape, and that's when I will see a decrease in this mass. Now, some of you will be wondering, why, Ms. Selina, that it is a curve here and why is it not a straight line that look like this? Well, let me explain to you further. As we know just now, A plus B will give you C and D. One of them is actually a gas as a product. The graph looks something like this. Why is it not a straight line like this? Very simple. In the beginning, A and B has their own concentration. The concentration of A and B is the maximum in the beginning. That's why you'll notice that the graph is the steepest here. Eventually, it slows down and eventually it comes to a stop. So in the beginning point here, why is it that it is the steepest? Because at this juncture here, I also have the maximum concentration of reactants. Therefore, the distance between the reactants is very small, or I should say that they are very close. When the distance between the particles are closer, when they decrease, I actually lead to an increase in the frequency of collision. So in the beginning, you have the maximum concentration of reactants, therefore decrease the distance of the reactants. And when the reactants are very close together, you actually increase the frequency of effective collision, When the collision increases, rate of reaction increases. Now, then why is it that as they go down, it becomes less and less and less? Because the reactants are reacted to form product. Therefore, the concentration of the reactants decrease. When it's decreased, the distance between the reactants is further or increases. Therefore, they decrease the frequency of effective collision. Therefore, rate of reaction decrease. And when it comes to a stop, why? Because the reactants or have already completely react to form your gas. And why is it doesn't go to zero? Remember, just now, this whole thing is placed in a measuring pan. So this one, I'm measuring the mass of all this, the reactants and the products over here. Why is there still a certain amount here? Because though the gas escaped, I still left with some of my reactants that's left over, that's unreacted, as well as the product that's C. That's why you flat line over here at this point. The difference here will in fact show you the mass of the gas. Another way to represent this graph is I can represent in this manner to show that this is the volume of gas that's collected. Actually, it's the opposite of this graph. Instead of seeing it in this manner, in the beginning of this experiment, it will be zero amount of gas. As the time goes by, the amount of gas increase until they come to a stop here. Now, what are some of the ways that, like I said just now, in the beginning is the maximum concentration of reactants, that's where the reaction is the fastest. Are there other factors that will make this entire rate of reaction happen faster? Yes, they are. These are my 5 factors. Okay, let's go through it one by one. First, increase in temperature. When temperature of a chemical reaction increases, I actually increase the kinetic energy. When the particles have more energy, I will actually increase the frequency of effective collision. When effective collision increase, rate of reaction increase. How about concentration? As we know, when the concentration increase, the particles are really close. When the particles are very close together, when the distance between the particle decrease, the distance between them decrease, I will tend to increase the frequency of collision. When the frequency of collision increase, you increase the rate of reaction. Similarly, when I talk about surface area, I'm comparing between powder and lumps of powder. Okay, so powder, the surface area exposed is larger, but as compared to lumps or balls of the reactants, obviously this will increase the rate of reaction. Why? When surface area increase, I decrease the distance between the particles because the particles now are closer together. Therefore, I will increase the frequency of collision, therefore increase the rate of reaction. How about pressure? When they have a higher pressure, when the gases are really packed together, same thing, I decrease the distance between the particles. When the distance between the particles decreases, I increase the frequency of effective collision, therefore increase the rate of reaction. Last but not least, if I add a catalyst, I actually lower the activation energy. So the particles doesn't need to collide so much to attain that energy, and they will have the reaction take place very fast. But of course, for this portion here is solely for pure sciences. Now, let's take a closer look at the different graphs and how these factors will affect my graphs. So for example, or for instance, if I increase the temperature, obviously this graph over here, I will complete this reaction faster if I increase the temperature. Let's say in the first place, I complete this reaction at 5 seconds. If temperature increase, I will complete this at 3 seconds. So the graph will look a little bit like this. I make sure that I have the same volume. Volume doesn't change. It will end at 3, so it will go all the way down and flatline here. Similarly, if I use this graph over here, to represent. If this is at 5 seconds, and if it's 3 seconds, because I increase the temperature, everything happens faster, it will look like this. How about instead of increasing temperature, I decrease the temperature? I make this reaction happen slower. Now, if the reaction happens slower, instead of 5 seconds now, perhaps they will end at the 7 seconds. So it will look like this. Similarly, the other graph will look like this. It will take a longer time to complete. Instead of ending at 5, it ends at 7 now. For both of the graph, you notice that it only gets less if I change any one of this factor, whether it's temperature, surface area, or pressure, or even add a catalyst. You will notice that I will change the shape of it. Either they end slower or they end faster. Slower, faster. There's one factor that will change the amount and also the speed of it that will take place. So what is that factor? That factor is actually my concentration. What do I mean by that? Let me show you. Over here, if I change the concentration of a chemical reaction. Now, imagine concentration for the first experiment. The concentration is 1 mole per dm³. The second experiment, let me use another color. For the experiment 2, instead of using 1 mole, I'm going to use 2 mole per dm³. So this is experiment 1. This is experiment 2. Now imagine, how do I make sense out of this? Very simple. Imagine, okay, experiment 1, you are trapped inside a train. And in this small little tiny train, there's a lot of zombies. The zombies are going to attack you. For 1 mole per dm³, the number of zombies is less than the 2 mole per dm³. 2 mole per dm³, you have more zombies. This have lesser zombies. Let me ask you a very simple question. For which one will you have more bites? And the chance of you getting beaten is the highest. Obviously, it's experiment 2. Not only you will be beaten faster, you will have even more bites on your skin. So, let's look back at just now that question regarding the volume of gas. Imagine that this one over here, the purple line, represents my 1 mole per dm³. So I'm going to transfer this over to this part so that you all have a better understanding. So I'm going to transfer the purple line to over at this portion here. This represents 1 mole per dm³. Experiment 1. Zombies are lesser bites. But now, because I increase the concentration to 2 mole per dm³, I have more zombies, the bites are even more. So not only that I will get beaten up faster, I have more bites. So the volume of gas will also increase. Can you see that I end at a faster time? Let's say this is 5, this is 3, and not only that, I double the amount of volume of gas that is formed. So when we come to concentration, just remember these zombie examples. One with lesser zombies, less bites, slower. More zombies, more bites, and even faster. So this is concentration. Because in concentration, remember, when the number of particles increases, the distance between the particle decrease, therefore increase the frequency of collision, therefore the rate of reaction increase. Next up, we're going to show you some of the examples from past year papers. Hey, thank you so much for watching through the entire video. I hope that you have benefited you, and remember to really understand the concept, because I can tell you, you'll be very, very useful in future when you continue to learn more about science, okay?